Welcome back to this tutorial of a von Karman vortices study with Code Saturn. In the previous video, we created a geometry and a mesh for the flow. Now it is time to create and set up a Code Saturn study. We will then launch the simulation to post-process the results on the paravis module of Salome. We are going to create a Code Saturn study. To do so, type the command Code Saturn create -s von Karman, or the name of the study, -c case 1. This will create you the von Karman folder. First, you want to move the mesh you just created into the von Karman/mesh folder. Once this is done, you can open the Code Saturn interface by typing Code Saturn GUI and then von Karman case 1 data setup.xml. This will automatically open the Code Saturn interface and select the folder you just created. Go in Mesh and press plus to open the Mesh folder. You should find the mesh you just moved here. Now, we are going to do a pre-processing only of the mesh. Run Code Saturn only by doing pre-processing and name the study Preproc. Save case and run. Pre-processing the mesh is useful if you want to set up the boundary zone. Instead of manually adding them and naming them, we can directly use the result of the pre-processing to load everything that was created in Salome. So go into Preproc that has been created into the residue folder and open the preprocessor.log. All of the groups that has been created before are now created in Code Saturn. You can rename them. Let's rename them with the name they had in the mesh. Don't forget to save the study. Now we're going to move into calculation feature. Standard Eulerian single phase, incompressible. We don't want to add any thermal body, any body forces, but in turbulence model, we're going to pick K epsilon. We are not putting any gravity, so we're going to unpick the gravity terms, and we don't need any wall function type, so let's put no wall function. We're going to set the velocity scale to 5. We don't transport any species, so now we're going to move on. In volume condition, go to all cells and set the density to 1 and the viscosity to 0.001 in order to have a high enough Reynolds number. In boundary condition, we're going to define the nature of all of the groups we created in Code Saturn. So the walls are, of course, wall. The inlet, we are going to change it to inlet. Outlet, we're going to change it to outlet. And symmetry to symmetry. And in inlet, we're going to set a velocity of 5 meters per second. The hydraulic parameter is 4 times the surface of the inlet divided by the perimeter. In our case, for the geometry we define, is going to be 0.17 approximately. Now we're not going to change the wall. We are letting it as a smooth wall. We don't have to change anything in the outlet and symmetry section. In time settings, we're going to put a reference time step of 0.025. The stopping criterion is going to be set until physical time of 15 seconds. We don't have to change anything in start and restart. And will not modify anything in numerical parameter nor in equation parameter. Let's go into post-processing and add an output every 5 time steps. To visualize the results in real time, Don't forget in the Writer tab to add in results output every n time steps. I put it to 5. In the mesh section, we are going to add all of the boundary zones we defined earlier in Code Saturn. Adding these here will allow you to visualize the associated areas of the mesh when post-processing. We are not going to change anything else. So now we can start to run the computation. Press on the Run Computation button, and this time we are going to execute our case study. Press Save Case and Run Computation. Now it's going to open this panel to show Code Saturn is currently working. You can click on Convergence tool to observe in real time the value of the residue. You can set the number of subplots to 1 and press refresh to see the value of the residue at the current iterations the code is. The residue are high in the beginning because the code is initializing the flow. And here are the residue I get at the end of the simulation. They are a bit high, but we are simulating unsteady flow, so it's possible. Let us now post-process them on paravis. Open Salome. You can either create a new study and save it, or open the one we did before, in which we made the geometry and the mesh. Once you're in Salome, go into paravis, and in the pipeline browser, right-click and select Open. Go into the folder of the study, here it's von Karman, and into the case that you created. Then go into the Resu folder, and you should find here all of the run you made with Code Saturn. Open the one that converged, in my case it's exact, and go into post-processing. Here you will find all of the data generated by Code Saturn. For each of the boundary zones defined earlier, you can find a results, then the name of the boundary. So you have the results inlet, results symmetry, and so on. We are going to look in details to the fluid, so let's open the result fluids domain.case. Here we are looking at the pressure of the mesh, so let's set it to the velocity. You can change the time iteration here. When launching the animation, we see the progressive formation of the von Karman vortices. We are now going to apply some filter to better visualize the results. Click on the results in the pipeline browser, and then you should see filter here. Go into alphabetical, and it will display all of the filters that are currently in paravis. From there, you can select the cell data to point data filter. This filter makes mapping from the mesh to a more smooth function, allowing you to smoothen the velocity profile. Now, once you have done this, we're going to create a glyph filter. Go into filter, search, and then you can type glyph. Here it is. Select it. As a scale, you will put no scale array and put a scale factor of 0.04, for example. And as an orientation, select velocity. Press apply. We have now generated arrows that are going to follow the velocity profile. The color scale here is wrong. It is displaying the color scale of the pressure. So go into coloring and change it to velocity. We can make the arrows a little bit bigger. Let's say 0.08. And there we have. So you see that even though we define only one cell element, it's not exactly 2D since we have in reality two places where the computation is performed. But for now, we are going to set the view only on this side. Finally, we are going to plot the velocity lines of the flow by creating a new filter. Select the cell data to point data filter, as it's going to be the input of this new filter, and click on this button. You can also look for the stream tracer filter, as we did before. Here, the filter is going to ask you to create a line that is going to be crossed by all of the streamlines of the flow. We are going to set it to 0, 0, 0, 1. So we are going to be in a 2D plan. And as a second point, let's set 1, 0, 41, 0, 1. Press apply. Here you can see all of the line of the velocity flow, but the coloring is not good. So make sure you have the velocity color map selected. You can change the number of streamlines here by tuning the resolution. Now, if you display both the streamlines and the glyph, you can have a nice view of the flow. And let's play the animation again. Now we clearly see the von Karman vortex forming here, with an alternating curl. For instance, let's stop the animation. Depending on the instant, you can see vortices spinning in alternating curls. And there we have it. We have observed the von Karman vortices with Code Saturn. Thank you for watching this video. If you have any questions, feel free to contact us on our website, on the GitHub, or to write any comments to give us feedback on this video. Goodbye.